Right, so thanks for your attending. Today I'm going to talk about our recent project on the light control thin film backscatter device using additive manufacturing. I'm Boxuan here from Aalto University. So here are some background information of the research. So because of the ubiquitous configurable lighting, such as LEDs, support the sensors to transmit the data through the optical wireless channels, known as the visible light communications, VOC, enable the Internet of Things. But the receiving front end, for example, the photodiodes and the photodetector, that is still lacking in most of the kind of portable receivers. But the ambient backscatter communication is the low power IoT technology that enables the device to transmit the data. We are modulating and reflecting the incidence RF signals from the environment. The backscatter device, BD, is responsible for harvesting, modulating, and reflecting the incidence RF signals from the sources, ambient RF sources. The data originated from the sensors are sent using the VOC and is converted to the electrical control signal at the backscatter device. And the backscatter device then transmits the data by modulating and reflecting ambient RF signals. So in this paper, we designed a thin film backscatter device that receives sensors data from the LEDs and transmit the data to the RF receivers at the 2.4 gigahertz SM band. We manufactured the backscatter device through the additive manufacturer, including inkjet printing, surface mounting, photonic curing, and oven curing. So we evaluated the backscatter device response to the various modulated light illumination without the ambient light interference, and we evaluated the BD frequency response to the LEDs. So here's the system model where the data sensors data are embedded into the modulated lights, and it's received by the backscatter device in the solar cell. So the photovoltaic conversion happens, and then the transfer the light to the energy and the control signal of the RF modulation. So the RF modulation modulate this carrier wave from the ambient RF sources and then send the backscatter signal to the RF receivers. This is the design of the backscatter device. So the upper one is the manufactured prototype. As you see, it's kind of compact and thin. And the lower side, we have the schematics that is composed of the circuitry and the coplanar waveguide patch antenna that is used in the previous study of our the research. So basically, the solar cell converted the electrical signal that is converted to the green one, the solar cell output, and after the low pass filter, it is compared through the comparator. An output of the comparator that is control signal of the RF switches that are switching the antenna terminations, and then to the modulations here. So the principle is quite simple. So we actually used modulator that is an RF switch connected to the antenna, switching the termination of the antenna as the short or open. So here's the additive manufacturing process that we used. It's a kind of low cost and using the inkjet printing, photonic curing, and then the SMD mounting the SMD components such as the comparators, RF switches, and some impedance matching circuit components. And lastly, we cured the adhesive proxy in the oven. So this is quite a kind of simple procedure. And here we show that there's the real-time data transmission demo setup where we put the LEDs that is controlled by the data that is generated in the function generator that is used to FSK signal symbols. And here the light is received by the backscatter device, put on the table. So we have the transmitter antenna that transmits 2.4 gigahertz carrier wave and received by the backscatter device to the modulation, and finally received by the RX, that is the real-time spectrum analyzer. And also we put the probes of the oscilloscope to monitor different output voltage at the backscatter device. So here's the time domain and frequency domain monitoring in this setup. In the left side, we have the oscilloscope probes in different positions of the backscatter device. So the solar cell output that you can see, that is the the PV converted signal that is to FSK. That's the packet information that is composed of the beats sequence, and then after the low pass filter, it's kind of DC level, and the comparator output the control signal that is that can recover the message, and then it do the modulation with the ambient RF signal at 2.4 gigahertz, and at the right side we have this spectrogram that includes the central frequency or carrier components. And then we have the FC plus minus F1 and 2, that is the two frequency components of the 2FSK signal, where we see the packet also in the received signal, and it's different in the time domain, in the different time slots. So here we do the capitalization of the illumination intensity response. So the left side, we change the illumination intensity of the modulated light from 100 to 1000 lux. So as the increasing of the light intensity, modulated light intensity, the DC and AC level are increasing. But most important thing in the right side is the RF switch control signal. That is also the comparator output. We have to make sure that the high level of the voltage that should be higher than the lower bound here. And also the low level should be lower than the upper bound here. So if you can see that at 100 lux, if we only have the light that is not interfered by the ambient light, so it works fine. But if you have the interference from the other two ambient light, that is also the LEDs and the office ceiling lights at different illumination level, it's crashed the performance. But from 200 lux to 1000 lux, so it's kind of performed well. So also we do the characterization of the modulated light frequency response, where we have different modulated light intensity. So we can see that at the very low level of the modulated lights, the frequency, the modulation frequency is also low. It's below 10 kilohertz. But at the kind of higher and higher of illumination, that we have up to 144 kilohertz level. And also the interference from the ambient light is kind of diminishing. And also we do the over-the-air backscatter propagation in a test in the anechoic chamber and the office corridor. So here we put the backscatter device that is moving between the transmitter and receiver, and also illuminated by the LEDs always. So in the chamber, there's no ambient light, and in the office corridor, there are kind of office ceiling light. So we use the backstatic dislocated model of the backscatter propagation that is very famous in the RFID literatures and the backscatter communications. And we use the realistic parameters, that is basically the measurement equipment parameters. And here's the measurement results and simulation result comparison. We have the you see that in a measurement in the anechoic chamber, that is quite similar trend with the simulation, but in the corridor, there are kind of outliers because of the kind of rich scattering environment in the corridor because of the reflection, scattering, and refraction, for example. So in this case, we validate that this backscatter propagation is kind of fulfilled the theoretical model. And in summary, in this work, we designed a thin film backscatter device that receives sensors data through the LEDs, that is optical wireless channels, and transmit the data to the RF receivers. So we kind of build a bridge between the VLC and the RF communications. And we manufacture this backscatter device through the simple low-cost additive manufacturing method. And we evaluate the backscatter device response to the barrier modulated light illumination. And we also evaluate this frequency response to the lights, showing that the maximum modulated rate can goes to 140 kilohertz. And also it depends on the solar cell and the arc reaches and the circuit that we used. Of course, we can reach to higher and higher frequency, but it depends on the use cases. For example, maybe it's enough for the low power and low rate IoT applications. So finally, we demonstrate over-the-air end-to-end sensor data transmission in the chamber and in the office corridor, and validated with the backscatter propagation model. So it means that this kind of device can be kind of potential to facilitate the combination of the visible light communication and the Internet of Things in the future wireless networks, that kind of more fusion in the 6G and the following So thank you very much for listening.